Before the 17th century, we had this massive problem. The universe was obviously in constant motion, right? Planets were moving, things were falling, but we literally didn't have the math to describe it. To really get a handle on things like gravity or orbits, or just the very idea of change, humanity needed something completely new. A revolution. We had to invent a whole new language for the universe.
So let's just dive right in. And believe it or not, the entire journey that lets us calculate something as complex as a rocket launch, well, it all starts with a 2,500-year-old brain teaser, a riddle that seemed to prove that motion itself was totally impossible.
So let's start right there, with that seemingly impossible motion. Our first section is all about what I like to call the impossible race.
Okay, so our story kicks off way back in ancient Greece with this philosopher, Zeno of Elea. And look, he wasn't just trying to be a troll. He was genuinely posing this deep, profound challenge to everything we think we know about reality.
So here's how the paradox goes. You've got this famous race between the speedy hero Achilles and a slow and steady tortoise. To make it fair, the tortoise gets a head start. Now, for Achilles to catch up, he first has to get to where the tortoise started, right? But in the time it takes him to do that, the tortoise has crawled a little bit further. Okay, no problem. Achilles now has to cover that new distance. But wait, in that time, the tortoise has moved forward again. You see the problem? This just keeps happening forever, with smaller and smaller gaps. Zeno's conclusion was just maddening. He argued that because Achilles has to complete an infinite number of little tasks, he can logically never, ever catch the tortoise.
And that right there is the real heart of the issue. This wasn't just some clever party trick. Zeno was the first person to really show that our basic gut feelings about the whole concept of infinity were just wrong. We're talking deeply, fundamentally flawed. And for more than 2,000 years, this puzzle was a serious roadblock for philosophers and mathematicians.
Okay, so let's hit the fast-forward button, jump ahead 2 millennia. By the time we get to the 17th century, Zeno's abstract little puzzle isn't just a philosophical debate anymore. It's become a very real, very practical barrier to understanding the universe, a universe that is very clearly in motion.
See, by this point you have absolute giants like Johannes Kepler doing all this incredibly detailed work. They knew the what. They had figured out that planets move in ellipses, not perfect circles. They knew their speeds change as they orbit the sun. Kepler had basically written the rulebook for how the solar system behaved. But, and this is a huge but, knowing the rules of a game is completely different from knowing why the game works the way it does. Nobody could explain the why.
And this was the core of the problem. The mathematical toolkit they had, it was a language for taking snapshots. Think Greek geometry. It was perfect for describing things that just sit there, things that are static and unchanging, like a square or a triangle. But the universe, as we know, isn't a snapshot. It's a full-blown movie in constant motion. Science was desperate for a new kind of math, a new language that could describe flow and change and all that movement.
And, well, you know what they say, necessity is the mother of invention. And in this case, that necessity gave birth to one of the single greatest inventions in the history of human thought, a true language of change.
And here's where the story gets really interesting. The problem was so ripe, so urgent, that the solution was basically invented twice, at almost the same time by 2 different geniuses working completely independently. You had Isaac Newton over in England, who was obsessed with a very concrete problem, gravity. And then you had Gottfried Leibniz in Germany, who was coming at it from a more abstract, philosophical direction. And what's amazing is that both of them, on their own, came up with the same revolutionary tool, calculus.
So what exactly is this big idea? Let's break it down with a simple example. Forget about planets and gravity for just a second. Just look at this bizarre, curvy line. How in the world do you measure the area underneath it? Old school geometry, your squares and circles, it's no help at all.
The truly genius insight was to just stop trying to measure the whole complicated thing at once. Instead, you do something clever. You slice that area up into a huge number of really thin rectangles. Now, finding the area of one simple rectangle, that's super easy, right? Length times width. So you calculate all those tiny areas and add them up, and you get a really close approximation. But, and this is the magic leap, what happens if you make those slices infinitely thin? Well, your approximation suddenly becomes perfectly, 100% exact. That's the core idea.
But that wasn't even the biggest aha moment. The real breakthrough, for both Newton and Leibniz, was realizing that this whole process, summing up an infinite number of tiny slices,
which we call integration, was the exact mathematical opposite of doing something else, finding the rate of change at a single instant. Think about the exact speed on your car's speedometer right now. That's called differentiation. And discovering these two things were linked, wow, that was the master key. It's like finding out that addition and subtraction aren't two different things. They're just two sides of the same coin.
But, of course, a discovery this massive, this world-changing, well, it wouldn't be a human story without some serious drama.
So the big question became, who invented it first? And the answer is, well, it's complicated. Newton actually came up with his version way back in the 1660s, but he was famously secretive and just didn't publish his work. Then, a bit later, Leibniz developed his own version, completely on his own, and he did publish it first in 1684. And what happened next was this ugly, bitter public feud. Supporters of Newton and Leibniz started accusing the other guy of plagiarism, of stealing the idea. It got nasty. Today, though, historians are pretty much all in agreement. They were independent co-discoverers, simple as that.
So while they and their followers were busy arguing over who got credit, the rest of the world was getting this incredible new tool. And their creation, this thing called calculus. I mean, it's been called the greatest advance in mathematics since the time of Archimedes. We're talking a nearly 2,000-year leap forward.
Okay, so now humanity is armed with this unbelievably powerful new tool, and with it, we could finally start to crack the code of the cosmos.
So, let's go all the way back to the beginning. What about Achilles and the tortoise? Well, calculus delivered the final knockout punch to that paradox. See, Zeno's big mistake was just assuming that if you add up an infinite number of things, the total has to be infinite. Calculus proved that's just not true. You can have an infinite series of smaller and smaller numbers that adds up to one single finite number. Just like 1/2 plus 1/4 plus 1/8 and so on adds up to exactly 1. So all of Achilles' infinite little steps, they add up to a finite distance, which, guess what? He covers in a finite amount of time. Problem solved.
And with that ancient puzzle finally put to bed, Newton could get back to the main event, the planets. His law of universal gravitation was a brilliant theory, but before calculus, that's all it was, a theory, an idea. But with calculus, he could actually prove it. He could show, with pure mathematics, that his law of gravity would cause the planets to move in the exact elliptical orbits that Kepler had so carefully measured all those years ago.
I mean, you really can't overstate how huge this was. This was a fundamental shift in how we saw the universe. All of a sudden, the heavens weren't some mysterious, mystical place run by unknowable forces. They were a grand mechanical system, a giant, intricate clockwork that was rational and predictable and whose rules we could actually understand.
And the legacy from that point on is just staggering. First, it became the absolute mathematical bedrock for all the engineering that powered the Industrial Revolution.
Then, centuries later, it provided the essential concepts that a guy named Albert Einstein would need to build his mind-bending theory of general relativity.
And yeah, to bring it right back to where we started, calculus was the hidden engine that powered the space race. Every single rocket launch, every orbital calculation that took us to the moon, absolutely none of it would have been possible without this language forged way back in the 17th century.
So here's the big takeaway from all of this. Sometimes, when you're faced with an impossible problem, you don't need a better answer, you need a whole new language just to ask the question in the right way. And that really makes you wonder, doesn't it? What impossible problem are we staring at right now that's just waiting for someone to invent its new language?